Hello and welcome. In this video, we're going to focus on three main things. We're going to talk about definite versus indefinite integrals. What are the differences between the two? We're going to talk about properties of definite integrals. And we're going to talk about how to find a Riemann sum. If you're not given a graph of a function, how to find it using a table and using different sort of factors than we have in the previous videos. But make sure that you've watched the previous videos about Riemann sums before you jump into this one. So let's go ahead and get started. Okay, so here on the left-hand side, we have definite integrals. A definite integral, some key features about it. A definite integral has bounds, meaning that it has an a and a b value. It has bounds that show up on the actual integral, one on the bottom, the lower bound, and one on the top, the upper bound. When we find or when we evaluate a definite integral, our answer is going to be a number. What we've been doing so far is approximating a definite integral using Riemann sums, but we have still gotten down to a number. This is approximately 9 units squared. So our answer, or after we evaluate a definite integral, we're going to have a number. And a definite integral, what it represents, is the area under a curve bounded by the x-axis. Now, indefinite integrals, which we haven't talked about in a couple of videos, do not have bounds. There are no numbers on the integral symbol. When we evaluate an indefinite integral, what we get is the antiderivative as a function with a plus c value. And what we're thinking about when we're evaluating indefinite integrals is what did I take the derivative of in order to get that integrand. So for example, if I look at the integral of x dx, what I would do is say, what gives me the derivative of x? Well, I would add 1 to that exponent, and I would divide by that value, and I would end up with a plus c. As opposed to something like what we did in a different video, we would say the area from 0 to 4 of some function is approximately 6 units squared, and we would be calculating that by finding the area of a certain number of rectangles. So it's important that you understand and recognize when we're talking about a definite integral and when we're talking about an indefinite integral. So when we talked about indefinite integrals, we talked about different properties that held true, how we could pull a scalar out, how we could split it into multiple functions if we just had two different terms being added or subtracted. And after we sort of introduced a lot of those rules, we started evaluating indefinite integrals to get our function. The same thing holds true with definite integrals. So what we're going to do first here is we're going to look at some properties of definite integrals that are really similar to the properties that we looked at before. There's a couple of them that are going to seem pretty new. And then we're going to practice using those properties. But instead of actually evaluating over a particular function, which we haven't really talked about how to do yet, we're going to be given some information, and then our goal is to use those different properties to manipulate what we have so that we can evaluate what we're being asked to evaluate. So first property, our sum and difference property. And this basically says that you can split up your integral into pieces based on where you have a plus or a minus. So for example, if I had the integral from 0 to 4 of something like 2x plus 1 dx, I could actually split that to be the integral from 0 to 4 of 2x dx plus the integral from 0 to 4 of 1 dx. The next property is the constant multiple property, and what that says is if we have some value inside being multiplied by our function, we can actually factor that outside, and we have seen this before, again, except without bounds on our integral. So for definite integrals, we could actually take this integral right here, and we could say this is the same thing as 2 times the integral from 0 to 4 of x dx. Obviously keeping this second one exactly the same. So that's what the constant multiple tells us. This next property is a little odd and only comes up in particular situations. But what this next property says is if you are integrating from a to b, but for whatever reason it would actually be easier to integrate from b to a, and we haven't really talked about why that might be the case, but to see how this property works, we're just going to assume that for some reason we need to. The only thing that we have to do in order to flip something is to put a negative in front. So let's say that we had the integral from -4 to -8 of some function f of x dx. Now, that is sort of weird to think about because -4 is actually smaller, or is actually larger than -8, so it would make more sense for us to be looking at the area from -8 to -4 of this f of x dx. If we wanted to change this, all we have to do is put a minus in front of the integral, and then we're allowed to flip the bounds like that. Again, this is something that might come in handy only under certain circumstances. The zero length interval property is this one right here. And this one says that if we're integrating from a number to itself, that area is going to be 0. And that should make sense. If I was integrating from the area under a curve from here to itself, right, there is no area under that curve because I'm not integrating over a particular amount. So if you're ever looking at an integral from a number to itself, that integral is going to be 0. The area under the curve in that case would be 0. And then last but not least, this last one, adding intervals, is sort of what I like to think of as the transitive property for integrals. If you are integrating from a to b and then from b to c, you can actually combine that as one big integral from a to c. So you can split, or in theory work backwards and unsplit, as long as you're splitting at the same value. So what this means is if I wanted to look at the integral from 0 to 10 of something, I could actually think about that as the integral from 0 to 2 plus the integral from 2 to 10. Because if I combine those two pieces, I'm going from 0 to 2 and 2 to 10, I'm still covering that whole area under the curve. And that should make sense because we're still looking at the whole area from point A to point B. So let's go ahead and practice using some of these properties with some given information. Again, the goal being here that we understand how to use the properties as needed. Okay, so for examples 1, 2, and 3 here, we are given two pieces of information. We're given that the integral from 6 to 11 of f of x dx is equal to -7, and that the integral from 11 to 6 of g of x dx is equal to 24. Number 1 is asking us to find the integral from 11 to 6, from 6 to 11, I don't know why I keep flipping that, from 6 to 11 of 9 times f of x dx. And what we just can do here is we can apply the constant multiple property, and we can say this is the same thing as 9 times this integral from 6 to 11 of f of x dx. And we know that this, based on this fact here, is equal to -7. So this is 9 times -7. So we can say that this is equal to -63. For number 2 here, we're looking at the integral from 6 to 11 of 6 times g of x minus 10 times f of x. So we're going to use a couple of properties here, the constant multiple property again, and also the sum difference property. So what we can say for this first piece here, 6 times g of x, is that this is equal to 6 times the integral from 6 to 11 of g of x dx. And then we can take this other scalar, this -10. This negative we can take out based on the sum difference property, and the 10 we can take out based on the scalar property, times the integral from 6 to 11 of f of x dx. Then we know that this is 24, and this is -7. So I'm going to have 6 times 24 minus 10 times -7, which is going to be 6 times 24 plus 70. 6 times 24 is going to be 144. 144 plus 70 is going to be 214. And there's actually an error in number 3. We can't divide, we can't simplify using division, so there's actually nothing that we can do on number 3. We're just going to leave it exactly like that. We can't just divide those two numbers because there is no property up here that relates multiplication or division. So there's nothing that we can do here on this number 3. It's actually good to stop and kind of notice what are we allowed to do and what are we not allowed to do. So go ahead and look at this practice example below. It says determine the value of the integral from 2 to 9 of f of x dx, given that the integral from 2 to 5 of f of x dx is 3, and the integral from 5 to 9 of f of x dx is 8. So go ahead and pause the video, work through that, and then unpause the video and see how you did. So hopefully you had time to work through that. The integral from 2 to 9 is going to be equivalent to the integral from 2 to 5 plus the integral from 5 to 9 because we're still covering that whole area. So this integral is just going to be equal to 3 plus 8, which means this integral is going to be equal to 11. All right, the last thing we're going to do in this video, I told you I was going to keep it short today, is we're going to look at finding Riemann sums from a table. So if we don't actually have a function or the graph of a function, we just have some selected information given to us in a table. So let's look at that. So all of the Riemann sums that we have calculated so far have come from being given a graph of a function or graphing a function and looking at the area under the curve by creating rectangles looking in that graph. In the real world, we often don't have a function to represent what we're talking about. Oftentimes what we have are data points and no other information, but we still may want to be able to get an approximation for whatever it is that we're talking about. In this case, we could either take the information that we're given and sketch a graph, which is a logical approach to take, although it may be time-consuming to sketch a graph so that you can come up with rectangles and find the area. The alternative is that we can use the information in the table as is to come up with the subintervals and the heights of the appropriate rectangles in order to calculate that area. And that's what we're going to practice here. And what I'm going to do is I'm actually going to create some more space, or we could just work through 4 and 5 down here. That's a better idea. So let f of x be a differentiable function for all x. Selected values, so there are more, but we're just being given some selected values of f of x are given in the table below. Use the data to approximate the indicated area using 4 subintervals. So notice it doesn't ask us to use 4 equal subintervals, and that makes sense because if you look at these x values, they're not changing at a constant rate. The first one goes from 0 to 6, then from 6 to 8, from 8 to 9, from 9 to 12. We aren't going to have equal subintervals here because the table doesn't give us enough information to do that. So what we need to do is use the 5 data points that we have to come up with 4 area approximations using the width and the height. So I'm going to do the best that I can to try and make this easy to follow here. So I need to cut these 5 data points into 4 sections. So one section is going to be looking at these 2 pieces. Another section is going to be looking at these 2 pieces. Another one is going to use these 2 points. And the last one is going to use these 2 points. So I basically have chunked this into 4 different pieces. Each piece is using 2 data points. So let's look at the first piece. The first piece being I'm going to call it the black piece for right now. This piece here, using the points 0, 7, and 6, 6. For number 4, we are being asked to use a left Riemann sum, which means the width I'm going to always calculate by looking at the change in the x values. So I'm going to make that note down here. The width is always going to just be the change in x. So if I look at the change in x here, that width is going to be 6. X is changing by 6. That's my width. And I need to multiply that by my height. My height in this case is coming from a left-handed sum, which means I'm going to use the left height, the left y value or the left f of x value as my height. So in this case, that's going to be 7. So if I was graphing this, the gray rectangle would have an area of 42. So now I'm going to look at the red one. Oops. The red one, our width would be the distance between 6 and 8. That width is 2. And the height would be the left-hand value, which is 6. 2 times 6 is going to give me 12. If I look at the blue one, my width from 8 to 9, that width is 1. And the height, using the left-hand value, is 8. So that would give me 8. And then last but not least, the green one, the width from 9 to 12 is 3. The height, using the left-handed piece, is going to be 5. So this is going to be 15. So if we add these all up to approximate this area, so we're saying, I'm going to write this over here now, the area from 0 to 12 of f of x dx is approximately what we get when we add all those numbers together, 42 plus 12 plus 8 plus 15. And if I add all of those numbers up together, I'm going to get 77 units squared. So this is definitely an approach that takes a lot of practice to get used to, setting it up, looking at which value you're supposed to use, drawing those little colored rectangles as I did. And for some of you, it may genuinely be easier for you to just plot each of those points, 0, 7, 6, 6. But again, this is going to spend a lot of time sort of creating a graph that's really not going to be incredibly helpful, but it could be useful if you're struggling to see it from a table. That is definitely an option. All right, let's go ahead and look at number 5. And I'm going to bring a new table in. It's the exact same numbers. I just wanted one that I hadn't written all over. We're going to approximate the same area from 0 to 12 using still 4 subintervals and using a right Riemann sum this time. So I want you to pause the video and see if you can identify, again, those 4 different intervals. So hopefully you've had time to do that. Our first interval is going to be these 2 points right here. So again, I'm looking at my width is going to be 6. And the height is now going to be the right side, which is 6. So that's going to be 36. If I then look at red, which is going to be using these 2 points, the width is going to be 2 from 6 to 8. I've moved 2 x's. And my height, again, is going to be the right-handed value, which is going to be 8. So that's going to give me 16. Looking at the next 2 values here, the width is 1. Looking at the right side for my height, that's going to be 5. And last but not least, looking at the interval from 9 to 12, the width is going to be 3, just like the same widths as there were before, because we're looking at the same table here. But our heights are now looking at the right-handed side instead of the left-handed side. So we could now say, if we used a right Riemann sum, the integral from 0 to 12 of f of x dx is approximately what we get when we add these numbers, 36, 16, 5, and 21 together, and that will give us 78 units squared. Something kind of interesting to notice, these approximations are pretty close together, which is interesting. We could do this using midpoint Riemann sums as well. That would be a little harder with this particular data set, so we're not going to walk through one like that, but we will definitely walk through one like that on a different day. So key things from this section. We talked about the differences between a definite and an indefinite integral. We talked about the properties of definite integrals, and we did some practice using those properties. And then we talked about how to find a Riemann sum using a table, breaking it into subintervals without having to actually create a graph. What we're going to do in the next section is we're going to talk about the fundamental theorem of calculus and the second fundamental theorem of calculus. And what that's going to allow us to do, the fundamental theorem of calculus, is going to allow us to evaluate a definite integral without having to use Riemann sums, which is going to save us time and it's going to give us an exact answer instead of an approximation. So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.